So here in this series of videos, we're going to be looking at undoing product rule. Uh, I personally find this to be the toughest of the derivative rules to undo because for me, I always want to try to use substitution, and this looks a lot like substitution. However, if I were to try just doing U substitution, it wouldn't work. And the idea here is it's called integration by parts, and it comes from the product rule if I were using Leibniz notation. So if I had this here and I isolate, this is just the product rule using Leibniz notation, u times derivative v plus v times derivative u. If I isolate the u times dv dx, I have u times dv dx equals the derivative of u times v minus v du dx. And then I integrated both sides with respect to x. The dx's will end up canceling, so I would have here the integral of u dv. Dx's cancel, and I would just have uv. Here, the dx's cancel, and I'd be left with the integral of v du. And that's where this notation is coming from. The key here is remembering that u and v are functions, and that means dv will be a function as well that happens to have dx in it. And it's trying to figure out what part of the integral should be u and what's left is dv. So this makes more sense once you see an example. So let's say I have the integral of x times cosine of x dx. I could try substitution here. I would not want u to equal x. And if I tried u to equal cosine of x, I wouldn't be able to get rid of all of the x's. And I wouldn't want u to be all of x cosine x. So substitution doesn't work here. So I'm going to try integration by parts. Ideally, what we do is we want to try to pick the u so that as we take the derivative over and over again, it will get closer and closer to 0, or some constant. So if I take the derivative of cosine, it's just going to bounce between sine, negative cosine, positive cosine. But the derivative of x is 1, so I'm going to try saying that u is equal to x. And so what that means is dv is what's left of my integral, which is cosine of x dx. So to figure out this integral by doing integration by parts, I need to know what's du dx, in which case that's 1, and then isolate du. And that's backwards from when we do substitution, when we isolate dx. When we're doing integration by parts, we want to isolate du. And then for dv dx, I want to integrate both sides so that I can say that v is the antiderivative of cosine, which would be sine. And I know this is an indefinite integral, but we're going to save the plus c for when we do our antiderivative of the original integral here. So this integral that we started with is now going to equal u times v, so x sine of x, minus the integral of v du, so the integral of sine of x dx. And so we haven't gotten rid of our integral entirely, but we do have an easier integral to work with. So I have x sine of x, then antiderivative of sine of x is negative cosine, so it's become plus cosine of x. And this is an indefinite integral, so I do need to remember plus c. And you can go ahead, if you want to, take a minute, pause the video, and check to make sure that this really is the antiderivative. But then sometimes we may have to do integration by parts a few times within a problem to get it down to an integral we're able to figure out. So for example, let's say we have the integral of x squared e to the x. So e to the x is, if I were to say that was u for integration by parts, its derivative is always e to the x. That's not getting down towards 0. if I say u is x squared, well, its derivative is 2x, and then if I derive again, I get 2, so that's a constant. So most likely, u is going to be x squared. So that means du dx is 2x. And if I isolate du, that's 2x dx. Then dv is what's left of my integral, e to the x dx. And then integrate that so that I can figure out that v is the antiderivative of e to the x, which is just e to the x. And I'll save the plus c for when I'm done with my original integral here. So this integral is going to equal u times v minus the integral of v du. So I've got the x squared e to the x. Now I have this integral here, and again, this isn't going to help me because I can't do u substitution on this. But I notice that 2x's derivative will go down. So I'm going to go ahead and do integration by parts on this integral here. And I'm going to say that my u is going to be the 2x. So du dx is 2, and isolate du, which is 2 dx. And then dv is what's left of my integral, which would be the e to the x dx. Integrate to find out what v is. Well, v is the antiderivative of e to the x, which is still e to the x. So now, for this integral, I still have this x squared e to the x I started with, but now minus u times v for the new integral, minus the integral of v du. Please note that when I did the second integration by parts, I do have to keep that in parentheses because I'm subtracting all of that. Well, this now is an antiderivative that I can figure out because the 2 can move outside. It's just asking what's the antiderivative of e to the x. So my integral is going to be x squared e to the x from our first integration by parts minus the 2x e to the x. Distribute that minus sign. This becomes plus. The 2 is pulled outside. Antiderivative of e to the x is just e to the x. And then I need to have plus c because this is an indefinite integral. And this right here is our antiderivative.